because that's going to be important on multiple questions on this thing. Question on this one, net ionic. All right. Which element has N equal 4 and L equal 2? This is talking about level and sublevel. Energy level 4 means 4 as far as electron configuration goes, and L equals 2 means D. Remember, L 0, 1, 2, 3 is SPDF. So L equals 2 is saying D sublevel. So one of these is going to be in that 4D series. And according to the periodic table, that's yttrium through cadmium, right? Knowing that it's 4D means it's somewhere in that segment. Fourth row of the D block. The top row of the D block, scandium through zinc, is 3D, not 4D. That's a common mistake as well. When you look at potassium and calcium and you know that that's 4S, sometimes people think that from potassium to krypton is the fourth row of the periodic table, and that everybody on that row is level 4, and that's not true. Remember, your D's are a little off kilter. You go from 4S to 3D, and then back to 4P. So scandium through zinc is 3D, yttrium through cadmium is 4D, it's going to be cadmium. Question on that one. Which compound reacts completely in water to form hydronium? Acid or base? What kind of compound forms hydronium? Acid. So this part is telling you that you're looking at an acid. And what kind of acid reacts completely, strong or weak? Strong. So that's really an elaborate way of saying which of these is a strong acid. Which of these compounds is a strong acid? And it's going to be HCl. Yeah. Okay. If it just said which of these compounds is a strong acid, then that's probably a 10-second problem for you. But worded like that makes you think a little bit deeper, a little bit longer. Question about it being HCl. All right, predict the products. Based on your reactants, what type of reaction is that going to be? Neutralization, because you got a base and an acid, correct? So aluminum hydroxide, hydrobromic acid, 3 hydroxides here, but 1 hydrogen there. That's not right proportions for neutralization. We need 3 hydrogens to counteract 3 hydroxides. That automatically means we're going to have 3 waters, right? Regardless of whatever else is going on. 3 hydrogens, 3 hydroxide, 3 waters. And what you have as your other product would be this 1 aluminum bonded with 3 bromides. That would be your other product. What kind of arrow? Well, it depends on your materials. What kind of base is this? Weak. What kind of acid is this? Strong. And the thing about neutralization was as long as one of them is strong, it's still going to be completion. They don't have to both be strong. If one of them's strong, that's enough to force the process and make it go to completion. Question about that? Is that all of them over there? That's all of them over there. Okay, so we got the molarity one left on the center board. Molarity by definition is moles per liter, so we take the molecules and convert to moles by Avogadro's number. And two significant figures, I'm getting 12. And that's in 0.4 liters. So 12 divided by 0.4, 30. Comes out to be 30 molarity. Question about that one? All right. Any questions on anything? Every single one of you needs to go back and look at naming too.
Look at what?
Naming. Compound naming. Which of those underlined parts is wrong? The dye, good. Because dye goes with things that are purely covalent, correct? And titanium, you know, is a metal. So proper name for that would be titanium 4 sulfate, correct? Yay, good.
I have a question. Why isn't that 2? Why isn't titanium 2?
Because sulfate is inherently a -2 charge, and you've got 2 of them. So the titanium has to offset all of that, and that's what makes it a +4.
So what if it was? I can't think of something, but if it was just, I thought that the charge of the thing in parentheses was what was going to be given.
Okay, now that's true, but you have to account for how many there are. That's 2 -2s. So collectively, that's 4 units of negative charge. Titanium 2 sulfate would be this. Titanium 2 nitrate would be this. Because nitrate is inherently -1. 2 of them would give you collectively -2. This would be titanium 2 nitrate. I don't know if that's any better or not.
Yeah.
But question on this? Any questions you've got related to naming? Eights and ites and hypoites, and acids, oxidation numbers? How are you with oxidation numbers? Comfortable? All right. All right.
Just lots of stuff.
It is a lot of stuff.
Remember.
It is. Yeah, I don't know what to tell you other than that. It is. But now part of it is stuff that we never got away from, and so there'll be some on there that you can answer very quickly, just because once we hit that topic, we never left it, and it's been through everything else that we've done. And there are other things that are kind of, I guess, more isolated topics. Let's try just a couple more, and then we'll do the phase diagram thing that we're supposed to be doing. Which compound has the highest boiling point? Highest boiling point.
C.
Not A. Anybody for B?
It's probably
Hydrogen bonding.
that's
Yeah.
the only thing I can think of.
This one has hydrogen bonding and the others don't. The thing that affects boiling point, melting point, vapor pressure, all that category of stuff was strength of forces, and hydrogen bonding was the dominant one, correct? And the way to identify hydrogen bonding is you have H to F, H to O, or H to N links. And people get familiar with hydrogen bonding when you're dealing with this, because you're accustomed to water, you're accustomed to things like this. But people forget about nitrogen as being hydrogen bonding. And so the answer is B, and it's because B is capable of hydrogen bonding and neither of the other two can. The last one has nitrogen and oxygen, but it doesn't have bonds between nitrogen, oxygen, no hydrogen, right? So there's no hydrogen bonding there. Question with are everybody okay with this being B? And B would also have, since it's got the strongest forces, it would have the highest boiling point, the highest melting point, the lowest vapor pressure, highest viscosity, highest surface tension, highest everything else that we talked about, right? It was vapor pressure was the one that was a little bit different. Because everything else was defined based on cohesion, whereas vapor pressure is defined on letting go. Those molecules of B are going to hold on pretty tight, which means they're not going to let go and they're not going to evaporate very much. Question with that? It is a lot of material to go back over, and the one thing that you want to do, and I probably said this before, but is to go over the things you got right first and brush up on them, just so that you don't make mistakes next week on things you got right earlier. And you make mistakes just because you hadn't looked at it in 2 months or something. All right? Brush up on what you're good at first, and then as time allows, go off into things that you were less good at. All right. All right. Just a little bit about phase diagrams. Phase diagrams are a graph of pressure. It's always pressure on the y-axis, temperature on the x-axis. And it's meant to show you what phase or what physical state you've got at any combination of temperature and pressure. Now this one is laid out for water. Your units on temperature are Celsius. On pressure, these are in torr. And so with your boundaries here, it's telling you what form exists at any set of conditions. And so if you wanted to know at 355 torr and 374 Celsius what form would exist, apparently that would be gas phase, correct? At that pair of conditions, it tells you what form you've got. And fundamentally, that's the main thing about this, is you don't have to do all these experiments, you can look at reference data. And the general form is always that pattern, that in your sections, as you're going, I guess, clockwise, it's solid, liquid, gas. So even if they're not labeled, you should know which area is which substance. If you forget that, you can always figure that out, because as you go across the x-axis and you're increasing temperature, temperature tends to make things turn vaporized, right? And so as you're going across increased temperature, you'd be turning solid into liquid and liquid into gas. So you can always figure it out that way if you forget the pattern. Solid becomes liquid, liquid becomes gas. Now, there is more stuff built into it. The only things that we really need to think about are this. Think about this segment right here. This boundary between liquid phase and gas phase. When you turn a liquid into a gas, that's called vaporization or boiling, correct? You can read this as what the vapor pressure would be as a function of temperature, or you can read the boiling temperature as a function of pressure. This entire section of the graph is boiling point. If you remember back when we talked about vapor pressure and things like that, we said the boiling point was not a point, but it's a function of applied pressure. You have a normal boiling point, which is based on 1 atmosphere, because that's normal atmospheric pressure. But boiling point itself is a variable. So that entire boundary between gas and liquid is boiling point. So I guess the boundary between solid and liquid would be a melting point. And that leaves us with a third boundary that we haven't talked about before. And that's the boundary between solid and gas. Directly between solid and gas without melting. Converting solid to gas without melting is called sublimation. And if you've ever played with dry ice, then you've seen what that is. Dry ice is called dry ice as opposed to regular wet ice, I guess, because it doesn't melt and puddle up like regular ice does. It goes directly from solid to gas phase. That transition is called sublimation. So each of those boundaries represents a change that can be at several different temperatures and pressures depending upon your conditions. Where they all intersect is kind of a special set of conditions called the triple point. At that set of conditions, all 3 phases coexist. And it's not that one is changed into another, they all just coexist. And you can see that truly is a point. There's one special set of conditions where you can get that to occur. And for water, that's 4.6 torr, which is very, very low, and 0.01 Celsius, which is barely above what would be your normal freezing point. Under normal conditions, water would be solid at 0, correct? This is a tiny bit above, but because the pressure is so low, you can actually have a little bit of solid there, along with the liquid and the gas. Triple point really is a point. There's another point out here called a critical point. And this is where you have a mistake in the graph that was printed. Notice you have that curve that goes up between liquid and gas. You get up to this point, but then the curve continues. It should not continue. It should go perfectly vertical at that point. Change that. It's still got it curving, it's still got it shaded beyond point C. That should not be the case. It goes completely vertical at that point. And the special thing about critical point is it's a permanent gas beyond that temperature. By definition, the critical point is the temperature at which only the gas phase can exist. Because all along this other part, as far as boiling point goes, so just for pretend if we start right here, we start at a set of conditions where temperature and pressure-wise this water would be liquid. If we heat it up, we can turn it into gas, correct? But if you squeeze on it and pressurize it, you can make it turn back to liquid. So that whole segment of boiling point is the competition between temperature, which wants to make it gas, and pressure that wants to make it liquid, all right? And in that competition between temperature and pressure, eventually temperature wins. And you can reach a point, you will reach a point, that's what the critical point is. It's just simply too hot, and no amount of pressure is able to liquefy it. So critical point is the temperature beyond which only the gas phase can exist. And regardless of pressure, you can't liquefy it. The only way to liquefy it is to back off on temperature. Flip the page. This one is a little bit more elaborate. You've got 4 regions as opposed to 3, but the cubic and the rhombic, these are 2 different crystal structures. So those are both solid. I guess a parallel kind of thing would be like a carbon. You can have carbon in the form of charcoal, you can have carbon in the form of diamond, right? That's 2 different solid forms of carbon. This is 2 different solid forms of something. I forgot what it was. But you got the different solid forms, and you got the liquid, and you got the gas. Which boundary or boundaries represent melting? What's the definition of melting? Turning what into what? Solid into liquid. So C to E is melting of the rhombic form, correct? And from E to F would be melting for the cubic form. Or you could just call that C to F, right? C to F is melting. Yeah, C to E, if you want to break that down into subsections, C to E is melting for the rhombic solid, and E to F is melting for the cubic solid. Boiling, C to D. What form would exist at 100 Celsius and 800 torr? Which solid? Rhombic, because you'd be looking at right about here, correct? What form would exist at standard temperature and pressure? Cubic. Because standard temperature is 0, standard pressure is right about here, 760 torr, correct? So we're thinking right up there, that would be the cubic solid. What form would exist at 180 Celsius and 1600 torr? Liquid? What form would exist at 250 Celsius and 1600 torr? Gas. What form would exist at 250 Celsius and 25 million torr? Still gas, because pressure don't matter once you get beyond, what, 210? Roughly 210? This is called critical point, but really it goes perfectly vertical at that point. No amount of pressure is going to liquefy it if it's above 210 degrees. You can't do it. The particles just are moving too fast, they're colliding and bouncing away. There's just no way for those attractions to kick in and liquefy. It can't be done.
I have a question. So on the exam, those are the kind of questions they'll be asking?
Sure.
How about if it's below zero? If the temperature?
Well, yeah, I mean, it starts here, but I guess you can have negative Celsius, so this would continue on, and this would just kind of continue at pretty much the same slope. You do have variables back in that part, okay, but I guess kind of pretend it continues on. The same kind of thing, pretend that this continues on at the same kind of an angle. You wouldn't be asked about things that are off scale in those areas. Now you might over there at the critical point, okay? Because this 25 million torr is off scale too, right? But that don't matter. That's not a problem because you know how critical point works. Question?
Yeah, so it can only be a gas under 500 torr, around 500.
At this temperature, it would take, yeah, about 500.
So anything
If the pressure were higher than that, if you were at 0 Celsius, pressure's higher than 500 torr would give you the cubic solid, but pressure's lower than 500 torr would be gas phase, because that's a sublimation process there. But all of this is the gaseous region. All right. Question about that? On a blank chart, you should know where solid, liquid, gas are. Even on the blank chart, you should know that this is sublimation, this is melting, this is boiling, because that's the pattern of your phases, right? As temperature goes up, solid, liquid, gas, transition.
So they're not going to label it?
Well, I'm just saying, if they're not, it's not a hindrance. You should know where they are. The sections may be labeled, the boundaries definitely won't be labeled. And so if you were asked which like we did there, which boundary represents boiling, you should be able to find liquid to gas and know that the boundary between them is boiling. That kind of thing. Or you could be asked, yeah, it'd be questions like this. What form would exist at this temperature and pressure? Those kinds of things. Question about these?